Today we shall start a new chapter, that is the chapter of recovery from failure. In any computer system, we are always subjected to failure. During processing, the power may go off, or the system may crash, or there may be a logical error, there may be a hardware error, there may be a software error, and various such error may occur for which the computing of a particular job may have to be halted. And while you are processing a particular job, in a normal situation, while you are running a program, the program is in the memory, and if your program is doing some work and suddenly power goes off, or the program crashes, or any other such thing occurs, we are at liberty to rerun the program and obtain our results. However, when we have a database system where there is a persistent source amount of data which is located into the disk, then there are a lot of potential problems that may occur. For example, consider even in a normal computer program, whenever there is a power failure, a lot of safety measures have to be taken so that the computer system, the operating system, etc., is not totally corrupted, and the system can restart from a proper and stable state. So recovery is there in each and every computer system, and in the case of a database system, it assumes a large amount of significance, or it is very important, because here there is some data which may be corrupted, and we must prevent corruption of that data during any system crash. Also, we must remember that if we have processed some job, and we should try to minimize our effort in terms of reprocessing of jobs. The first criteria is safety and security. The second is minimizing your effort. So we will study the topic of recovery from failure as it occurs in a database system. Such things occur in both operating systems, computer systems, hardware systems, software faults, file systems. So many problems occur. For example, if in a normal computer system suddenly the system fails and it has to go down, then immediately a lot of recovery actions are taken, and some actions are taken to indicate that these points have to be checked back when you restart again. For example, if your power goes off, then whenever you start your PC on a Linux or any other operating system, you will see that the file system is being repaired. So there are two or three types of actions which have to be taken prior to failure, during failure, and after failure. So we will have to see what happens and what we do in the case of a database system. To understand the concept of recovery and its importance, we have to try and visualize two very important things which is there for a database system. The first is the concept of atomicity and consistency, and the second is that of commitment. So let us see what each of them mean. Suppose we are working on a library system and we are doing a issue of a book or a return of a book, and when we return a book, maybe we have got to update it in two places. One is one table we have to update where the book information is there, and whether the book is currently available in the library or not. Suppose that is an information which has to be put. In one table we have to put in the date of return, so we have a table corresponding to book, and for every book we put in the date of return of the book for that particular user. And maybe in a user we will have to enter that date of return in the user table. Now, if these two places we have to do an operation, then whenever we return a book we have to write in two places. Now, what is meant by atomicity? An operation is said to be atomic if it can be executed only totally. It should not be partially executed. For example, if this operation, which is to update this and write in two different places, if it is stopped midway by chance, by intention, or by a crash due to failure, then the database may become inconsistent, because in one place there will be a date of return and in another place there will be no date of return. This is a physical inconsistency, because we must have the same value at two different places. Now, let us see a case of a logical inconsistency. The example which is often cited in the case of a logical inconsistency is that you are trying to put in some money, transfer some money from one account to another. So, in one account you will deduct X amount, and in one account you will credit that same X amount, and these two things you will have to update one field in account number X, and you will have to update another field in account A. A variable A will have to be updated in one table, and maybe an attribute B will have to be updated in another table. This will have to be added by X, and this will have to be subtracted by X. And this is a logical consistency, in the sense that if you do only one of them, then the operation is not properly or completely done. And if a failure occurs before this operation or after this operation, I am not bothered, because I am not so much bothered, because the database will not be inconsistent. But if a crash occurs here in between these two, then there is a possibility that the database will be inconsistent, because maybe here there was 1000 initially and B was 500 and X is say 30, then either you will have 1500 which is prior to both the operations, or you will have 970 and 530 which is after both the operations. If a crash occurs in between here, you may land up with a situation 970 and 500 which is an inconsistent situation. In a database design, we try to avoid this sort of inconsistency, in the sense that we try to have an attribute in only one place, a unique attribute. We do not try to write and update a value in more than one place. We normalize it so that if you update in one place, you do not have to update in 50 other places. But this sort of inconsistency cannot be immediately removed. This sort of consistency has to be kept. It cannot be removed by normalization. This is a logical case, and in such a logical scenario, whenever a particular job starts the process of money transfer, then we must ensure that this money transfer should be fully done. If this money transfer is halted midway, then the database may become inconsistent. So, the concept of atomicity is that a job is said to be atomic if it has to be done fully, so that the database remains consistent. It cannot be partially done and then the control will be handed over to somebody else. If you recall, in operating systems, whenever you are working on shared variables, the concept of atomicity is very important. If somebody starts working on a shared information, all of them should continuously work on a shared information. So, when we come to sharing of information, the concept of atomicity gains even more significance. Here there is no question of sharing of information. This is a process is working purely by itself on a particular data, and it may corrupt the data by finishing or aborting in midway. When we come to sharing of information, we will see atomicity due to sharing of information is another issue. In the particular topic that we are discussing, we will only consider single processes working on data. There are no shared data. We will discuss the concept of shared data when we discuss concurrency control. So, here atomicity means that a job is said to be atomic if it must be done fully or nothing. So, it is all or none at all is the concept of atomicity. And we must, whenever we are considering the possibility of a failure, we must ensure that jobs which are atomic are either fully done, or if they are partially done, then their effect has to be undone. The second, so this is the issue of atomicity. The second is the issue of commitment. The issue of commitment is like this. Suppose you are going to purchase a railway ticket in a railway reservation counter, and the program which is doing the railway ticket job, it works like this. It gives you a ticket, your ticket is given to you, and then it updates the database. So, you can well imagine what is going to happen if it issues you a ticket and then updates the database. So, after the ticket is given to you, the system power goes off. So, it just could not update the database, you have gone home with that ticket. This is a failure which can be blocked by maybe atomicity and by writing the code in such a way that your ticket is issued after your commitment, that is after it has been written into the database. So, this is a very simple way of tackling this problem. But suppose by chance or by any other problem, you are issued the ticket, it is written onto the database, and after some time by some other operation on the data, that file goes out. Then what do you do? Then you run into a much bigger problem. Your database portion has got corrupted because after you have made a commitment. So, how do we tackle that issue? Thirdly, in many database systems, suppose you are writing onto the database. So, that is fine that you have decided that you will write onto the database and then issue the ticket. But due to buffering, in which the page which exists, which is to be written into the database, is actually existing in the memory for the database buffering issue. We discussed the concept of virtual memory before, where we said that all the files are not directly updated at each and every instance. It is updated, it is kept in the memory, the data corresponding to certain files may be kept in the memory, and they may be updated when another portion of the data requires more buffer space. So, by a replacement policy they may be kept. So, due to buffering, if there is a virtual buffering going on in the system, then either you have to ensure that every time you make a commitment, you actually force output the data into the disk, or you keep certain other mechanisms under your control, so that even if the data which is not yet been written onto the disk and is in the memory goes out due to power failure, you can still stand by your commitment. So, we have to see, we have to take care of the two major issues of atomicity, consistency, and that of commitment. And in every case of fighting against failure, we have got two things to do. One is precautionary measures, action taken during normal processing to ensure retaining of sufficient information for recovery. That is, in the simple case, when the power goes off, you mark that your file system has to be cleared and cleaned as soon as the system boots up again. So, actions that have to be taken not only during crash, but actions that may have to be taken during the normal process of activity. You maintain some information saying that, oh, I have done this information, I have done this and keep it in a separate place. And finally, obviously, you have to take recovery action after failure. So, these are two types of things which have to be done. One is action taken during normal processing, so that you can recover after failure, and then how do you use this information to actually recover after failure. We have discussed before that the data is stored in various storage types. One is the volatile storage or the main memory. In the main memory, the data is such that it resides as long as there is power. Whenever there is no power, there is a system crash or any other thing. When the system goes off, the data in the volatile memory immediately goes off. However, data in the secondary storage or the disk is not volatile. Even if the system goes off, the data may remain there. So, whereas this is the corresponds to the main store, the cache and the other type of storage elements, this corresponds to the secondary store. The secondary storage remains in case of most system crashes, except crashes like the disk fails, the head really crashes and it just writes on to the disk, or the disk breaks or something like that, or some magnetic element goes through the disk and all the data is gone. So, some vague things may occur for which the non-volatile storage itself may become corrupted. Data in the non-volatile storage may become corrupted. So, you can also think of a utopian concept of a stable storage which never fails. A stable storage which never fails, such a situation is unlikely to actually happen, or you are unlikely to get something which never fails, but a stable storage can be conceived of a set of non-volatile storages which are written in 5 or 6 different places. If you will remember, there was an earthquake in Japan 3 years ago in a very big city which was an industrial town, and they had a number of computer linkages, and among two companies, one company collapsed the day the earthquake came and the other started operations in another city the next day. It was because the data, all the computer information and all the data which one company had was in that only one place, whereas the other one actually wrote it to 5 or 6 other places in Japan. And so, the next day they really could start off their operations with all their data intact. So, a stable storage can be conceived of a storage which has got high reliability. There are a number of such actual devices which you have. If you see computer technology, you have got RAIDs or dual disks in which you copy, you continuously write onto 2 places. You have got fault tolerant machines, fault tolerant memories, fault tolerant drives, so that they are able to sustain a lot of faults. So, a stable storage is possibly a set of interconnected secondary storages where you have got a lot of information. And among this, obviously, the volatile storage will be about the size of the address space currently. This will be a huge size. This is the size of the secondary store is much more than the main store, and the size of the stable store will be much less than the secondary storage. It will possibly be close to whatever is the main, because we would not like to write too many things onto the stable storage. If we have got a stable storage in which we can write thousands of data and millions of data of the size of a secondary storage, then we need not have a secondary storage at all. So, currently we will study what happens when the volatile storage goes off and the non-volatile storage is intact, in the sense that it may be corrupted, but it cannot be destroyed. Then we will later on see what happens, what we may do if even this gets destroyed. As we have discussed before, there are several types of errors that can occur. This is a logical error. a program floating point exception and things like that, in which the program crashes because of a logical error, and immediately when the program crashes or there is a logical error, the data corresponding to the program in the main memory aborts and the program aborts and there is nothing available. There may be system crashes, the bus may go faulty or the hardware may go wrong, and or even the software errors may occur. And there can be other types of crashes like power failure, which we call system crashes. These are system errors, errors due to software, system software, and we may have crashes like power failure, and we can have what we call a disk crash, in which the disk itself gets destroyed. For the time being, we will bother about the first three, and the first three are the ones which cause the main storage to be completely wiped out, whereas the disk storage is maintained. In order to understand what is the actual sort of inconsistency that can occur, we must try to see how data transfer takes place from disk to main memory. Let us assume that there are two types of operations which occur for transferring data from main store to disk. So, let us say we have got a main memory, and we have got the disk. Now, whenever we want to transfer data, we will assume that we do this through two operations. There are actually only two operations which interact, which cause an interaction between the disk and the main memory. The first is the input operation. The input operation, when I say input x, all right, and then I will say input output x. X is a variable. X is a variable which will exist as a record, as a field of a record or whatever. Now, input x transfers the block, because it is a block transfer from the disk. You can only get a block. When you write input x, then there will be a block in the storage, in the secondary store, corresponding to the place where x exists, and that whole block will be brought and written onto the buffer area of the main memory. So, that is the input function. And there is the output function. When you say output x, then the record x resides in a particular block which is in the buffer area. That buffer block will be written back to the disk. So, let us assume that we have got two operations, input x which brings, that is, which reads the block containing the variable x from the disk to the main memory, and output x which writes the block, the buffer block corresponding to the variable x, the full block is written back into the hard disk. So, these are the two operations which will be used by the system internally to communicate between the main memory and the store. The user will not perform these two operations. These we will assume to be system operations or operations of the core file system. The file system and the kernel will only perform these operations. The user or the person who has written a program will perform the two operations read and write. There will be two operations, read operation and write operation. The read operation will say read the variable or the record or the field x which resides in the disk into a variable xi. The action corresponding to read will be, if the record or the field or the value x is not already in the buffer area of the main store, then input x, and then assign xi to x. The write operation is, if x is not in the main store, then assign xi to x. The write operation is, if x is not in the buffer area of the main store, then input x. The assign operation is, if x is not already in the buffer area of the main store, then input x. The write operation is, if the record or the field or the value x is not already in the buffer area of the main store, then assign xi to x. The write operation is, if x is not in the main store, If it is in the main store, then x is assigned xi. If it is not in the main store, then bring it to the main store and then write x assigned xi. So, you will see that the read and the write operations will be performed using the input operations only. When you have to read, if it is not in the if it is in the main store, you will just read it from the memory. Otherwise, you will take the record, the whole block corresponding to the record, and read it into the memory from the disk, and then read it from the memory. If you have to output it, that is, if you have to write it into the disk, then you will have to bring the block, whole block where x exists, write the value of xi into the memory, and then wait for the buffering action itself. You just keep it in the memory in the buffer area. And how will it be written back into the disk? It will be written back into the disk as and when the operating system so decides. That is, the output function, output x, is used depending on the buffer management technique used. For example, you may not immediately write the value of x onto the disk. That, as we have discussed before in the buffering concept, will be written whenever the block corresponding to x may have to be replaced by another input operation. As long as it is not required to be replaced, it may remain onto the buffer area till all the operations are completed. When all the operations are completed for a particular total database, maybe then at the end of the session all the blocks may be written. Otherwise, unnecessarily we will have to perform too many output operations, because in the same block, by locality of reference, you will update data corresponding to the same block many times. So, if you start doing output operations after each write operation, then you may be wasting a lot of time just doing IO access. To prevent that, the whole concept of buffer management and buffering is used, and therefore, the output function will be used depending on the style of buffer management, the block replacement strategy, and other strategies which are there. So, this is another key which we have to remember, and we have to remember this because of our principle of atomicity and our principle of commitment. We may commit, we may commit after saying that the write operation has been performed, but actually it still may not be there in the disk. And if the power goes off, we are in a soup, because we have already committed, we have done a job, but still it is not written onto the disk. So, we have to take care of deciding when to write onto the disk and when to do each and every operation. We now see what is the property of a job. We normally, whenever we may give a query which will just read from the database. We may give an update operation, we may give an insert operation, or we may give a delete operation. And any job will be a combination of a query, update, insert, or delete operation. Now, we have to define what we mean by an atomic job. The user who is writing a program will decide on the atomicity, because the user knows what is the logical completeness of a particular job. Secondly, we will not allow a job to do certain unnecessary things. For example, if we have got a task T which is updating the database, we can give an operation read x xi, then we will say xi is assigned 12, then we will write x xi, then again we may want to read, after doing something else, we may want to read x xi, and again assign xi to some 15, and again write x xi. Now, there is a lot of inconsistency in doing this. This is a sort of a bad programming. Firstly, you are accessing the disk too many times. You need not perform this write operation at all, because whatever you do, the value of which you are going to write is always available to you in the memory. You are going to read this back again and write this back again, and this is a cause of potential problems, because you have read this data, you will write it partially, and this is one whole atomic job. You will write it in between and again read it in the middle, and you may land up into a number of problems which not only arise due to failure, we shall see these are even more complicated by the case of concurrency. It can be said that for any such job which is using more than one variable, or which is using any particular variable, it is sufficient to be able to write that job by reading it only once and writing the result only once. You can always do an equivalent job corresponding to this job by reading a particular variable only once and by writing that variable only once. You need not read and write it several times. So that makes the job not only simpler, it makes it easier for us to proceed with the analysis, and we will see later on, it reduces the overhead on recovery from failure because of simplifying a job like this. Such a job, an atomic job which has got a single read and a single write for any particular variable. If it uses 3 variables, then for each of the variables it can maximally read it once and maximally write it once. Such a job is called a transaction. There are two objectives of a transaction. It continuously maintains database consistency. That is, we will say a transaction must be executed in the full, and when a transaction is completely executed, we will assume that it maintains the database consistency if it is correctly executed. And secondly, we will say that a transaction is always of the form that the program unit that reads the required data items only once and will write them if they update it only once. If they do not change the data item, there is no need to write back that data. That is, if you are not required to change and write back the data, then you should not write back that data. That is quite obvious, but instead of reading it more than once, a transaction is a program item that reads the data item only once and writes them if required only once. And secondly, it maintains database consistency. So now we will consider for the time being every job to be a transaction, and if a transaction is fully executed, we will assume that a job is fully executed. Corresponding to every insert, delete and any consistent operation, you can define what is a transaction. In all query languages like SQL and others, you have got provision for definition of what is a transaction, which is a function which works on the data which is defined. This is the example of a transaction which really does a money transfer. Read the disk variable A into a memory variable A1. A1 is assigned A1 plus 50. Write the memory variable A1 to the disk variable A. Then read B into B1. B1 is assigned B1 minus 50. Write B B1. Even if this read and write for interchange, there would have been no problem, it would still be a transaction. You could as well read this, then update this, then update this, then update this, and then write the two. That would still be a transaction. A transaction just says that the job, according to the user, logically must maintain the database consistency, and for any one of the database variables, like A must be read only once and written only once, B is read only once and written only once. So, just to reiterate, the major features or requirements of a transaction are correctness and consistency and atomicity. Now, in order to study failure, that is, a system will fail, we have seen what type of failures can occur. We must also understand that there may be different stages at which a failure can occur depending on the job which is being performed. So, particular transaction is running. The transaction before it starts, if the failure occurs, that is one situation. After it starts and before it completes, the failure occurs, that is another situation. The transaction is completed, but all the output blocks are not written onto the disk. That is, the write operations have been performed, but their corresponding output operations have not been performed, and then a crash occurs. That is another situation in which a crash occurs. So, for every transaction, we should be able to identify when the crash occurs. For that, we need to define what are called the states of a transaction. We define the following states of a transaction: the active state, the partially committed state, the failed state, the aborted state, and the committed state. A transaction is said to be active after it starts and before the job is completed. That is, if this is a transaction, when the transaction starts, that is, the first statement of the transaction is being executed, and before the last statement has completed execution, the transaction is said to be in active state. A transaction is said to be partially committed if after the last statement of the transaction is completed. A transaction is said to be failed if there is any error occurring and the transaction is dropped, or there is an error due to any reason during the execution of a transaction before it is fully executed. Before we understand what is meant by failure, we must understand what is meant by fully executed. We say a transaction is committed if all the data corresponding to that transaction is actually written onto the disk, or some action has been taken to ensure that the data will actually be written onto the disk. The data may not be actually written onto the disk, but action has been taken to ensure that even after failure occurs, we will be able to recover from that failure. That is commitment. Partial commitment is the program is actually finished execution, but if an error occurs in partial execution, we will not be able to say that the job is done. Committed is a state after partial execution in which either the data has actually been written onto the disk or some other action has been taken, so that even if failure occurs, we will be able to say that this job is done. That is, we will say that after the data, say you are going on a railway reservation ticket, and when you start booking your ticket, it becomes active. After all the data has been entered and all the main memory processing has been done, it is said to be partially committed. It is said to be committed when either the data has been written onto the actual data into the disk, or some other information has been written in another place, so that you can be issued your ticket, and even if power goes off, from that other place I will be able to recover that I have actually issued you your ticket. I may not have written it into the actual place where the data is to be updated, but I have written it somewhere into the disk. So, we will see that concept of somewhere a little later. And if in between, before commitment, if the job is stopped due to some reason, it is said to be failed, and a job is said to be aborted if after failure you cannot go to any state other than restart the whole job. You just kill the job and restart it. So, there are the following states of a transaction. and this is the state diagram of a transaction. It becomes very important to understand especially these three states. Here the failure has occurred, but here a crash or of any failure may occur during active state, it may occur when it is partially committed, it may occur after it is committed, and the activities that will be taken for recovering from these three will be different. And what happens if it is failed or aborted? You have got only two options. The options are you either restart, that is the job is finished, you restart it, or you forget about it, that is you kill the job and say I will never do it again, or you restart the job. There are two options which you have. You can either restart the job and start it from the beginning, or you kill the job. So, if it is active, partially committed or committed and failure occurs, then we have to do something and then restart the job, that is we have to recover, and after we recover from an aborted job, we will either we will have to recover and then restart. So, if it is active, we recover by some means, if it is partially committed, we recover by some means, and if it is committed, then we recover by some other means. So, now next we shall see how we proceed with the whole business of recovery, what is the technique which we shall use for recovering from failure at each of these states. For this we will next study the log based method of recovery, that we will do in the next lecture.